I want to talk in more detail about just what goes on with this business of swing and trying to stay in a linear operation region. And so certainly this kind of region in here is where we want to be. That's in the saturation region, and as I say, that's where the amplifier would operate linearly. But what does that really mean? How do we stay in there? How do we ensure that? So limits would obviously, or some limits that you can see is point A, and where we would fall into triode and or cutoff, and point B if we go this way where we fall into triode, and here we fall into cutoff. So clearly those are our limits. I wish I could just do the undo on this. And I picked a different Q point. I've got a little bit different transistor than the previous example. So I've got VT is 0.4 volts. We got a VDD of 1.8 volts. UNC aux is 0.4 milliamps per volt, so 400 microamps per volt squared. W over L is 10. VGS at the Q point that I picked right here is 0.6 volts, which means we have a V overdrive at this point of 0.2 volts. So if we're at that Q point that I picked, and we know that we can write the composite voltage VGS of T, which is equal to big VGS, the DC value, not DS, GS. This full screen is nice, but it's kind of a nuisance too. VGS at point Q, plus the small signal part of it, little VGS of T. And so what we have is that if this is 0.6, so this would be 0.6 plus little VGS of T. And we need to keep VGS greater than VT, which is 0.4 volts. So we'll just say, okay, so 0.4, that's the limit for this composite voltage. It can't be any less than that. That would equal 0.6 plus little VGS of T, or we could say little VGS of T can't be any worse than 0.4 minus 0.6 is negative 0.2. We can't go any more negative. We can't go any, from this Q point here, we can't go any more negative than 0.2 volts on Vn. That's a minus voltage, right? So hopefully that makes some sense to you. We can't go any more than minus 200 millivolts. So that's the most we can swing to. That's the AC swing. And at that point, at little VGS of T is equal to minus 0.2, V out would be equal to VDD, or 1.8 volts here, because it's the point where we've fallen. If we've gone negative 0.2, then our output is up here at VDD, because there's no current in the transistor. We don't want that. That's a disaster. But it would. That is where it would fall into cutoff. So, one good question is, what would be the current at point Q? I'll just write it that way. Well, it's in saturation, so it equals 1/2 mu n C aux W over L times V overdrive squared. And V overdrive is 0.2 volts. So we've got 1/2 times 400 microamps per volt squared times 10 times 0.2 squared, and we get 80 microamps at that Q point. And then we can easily find V out, so V out at that Q point would be VDD minus IDRD, because this equals VDS at Q. That's what V out is. So we've got 1.8 minus 80 microamps, and I've said we've got 17K ohms for RD. So times 17,500. Put all those in. We've got 1.8 minus 1.4. It's a 0.4 volts. That's the output voltage here. Is 0.4. So what about at point at the edge of triode? Because that would be further limit our swing. Is what do we have for the operating conditions at that point, at point B? Well, so and so that's a place where we need to keep V out is greater than VDS, or if V out, sorry, that's not VS, V overdrive. If V out, which equals VDS, becomes less than, if it's, well, it's the place where it becomes equal to V overdrive, but if VDS is less than V overdrive, then triode. But that value is not 0.2. That's the V overdrive at point Q. We have a different V overdrive here because V overdrive is VGS minus VT, and we need to find that Q point there. So there's a miserable little formula in the text that you can use to find that. You can find it by iteration, but the book says VGS at point B is VT plus 2 mu n Cox W over L times RD times VDD plus 1, that's all in a square root, minus 1 all over, not all, but that part over mu n Cox W over L times RD. And if we put all those in, then we get 0.4 plus 0.213, and that equals 0.613. That's the VGS right there. And that would cause a V overdrive at point B of 0.613 minus VT, which is 0.4, or 0.213. Okay? And that should be VDS at point B, because that's the place where this happens, right? So VDS should be 0.213 at that place where we fall down to, or fall into triode if we go any higher in VGS or any lower in VDS. So we know up here at point A, we've got VGS is equal to 0.4. and VDS is equal to 1.8, which is VDD. And here we have VGS is equal to 0.6, and VDS would be 0.4. And then at point B, we have VGS is equal to 0.613, and VDS is equal to 0.213. So that would give us a swing between these of VGS would need to stay between 0.4 needs to be less than VGS, which is less than, which equals, I should say that equals Vn. And that needs to stay less than 0.613. Those are the limits that we have. To stay in the saturation region, we have these limits like that, and it's we just need to stay between that. But really, we should be centered at this point right here, and that would give us a smaller swing. We really need to be, we set our input voltage and then therefore the current and output voltage at a point Q, and let our signal move for around about that. So let's see if I can change the page here. So with that, if we centered there, then the max swing would be actually VGSB, the maximum input swing, VGSB, minus the Q point, VGS at point Q, which is 0.613 minus 0.6. So we would have VGS is in the plus direction. All that can go is 0.013. Right? So that's actually quite a bit less swing. And in the max swing we already had, the minus swing was 0.2. But if we want it to be symmetrical, if we don't want, if we want to be able to put in the same positive going signal as minus going, so that would be, we've got a VGS of Q, and so we're saying that we want a signal that is the same amount up as it is down. Then we would really have VGS of Q plus minus 0.13, 13 millivolts. That would keep us from falling into triode or cutoff, certainly. But that would go all the way to point B. It wouldn't go all the way to point A, which is good. But what is that output swing look like if we do fall that far? So VDS at point B is equal to 0.213. And at the minimum input, minimum, we've got VGS minus 0.013, which is 0.587. So that would be our input voltage. And so then we'd have a V overdrive min of 0.587 minus 0.4, which is 0.187. And so then we've got a current of 1/2 mu n Cox W over L V overdrive squared. So that composite current is 1/2 mu n Cox W over L V overdrive squared. If we put those numbers in using this, well, I'll just write it in. 1/2 times 400 e to the minus 6 times 10 times 0.187 squared, we get 69.9 microamps. Okay, so then VDS, our max output actually, so our maximum output would be VDD minus ID RD, which would be 1.8 minus 69.9 e to the minus 6 times 17,500. And that gets 0.576 volts. So our VDS from that Q point, we're swinging from 0.213 up to 0.576, or that is 0.4 minus 0.187 is less than VDS, is less than 0.4 plus 0.176. So we're plus 0.176 volts, and we're minus 0.187 volts. And that's really not quite linear, right? So a linear operation would mean if we have a plus 0.13 or 13 millivolt input signal, then we would scale that and have the same plus minus swing on the outputs, but we don't. It's not quite linear. That means we've got distortion. It means if we input a sinusoid and look at that output, it won't look the same. It'll be more curvy, and that could be a problem. So in the first case, I could say, well, we want to keep it below point A or below point B and above point A, whichever way you look at input or output, right in that range. But that's not symmetrical, so that would be a problem. So then we said, okay, well, we could limit our operating region to be right in here, but we still don't get a linear region. It's not really linear in that operation region. So we had the small signal approximation was plus or minus 5 millivolts, and on the input. But we used plus or minus 13 millivolts, right? We used plus or minus 13 millivolts, but the small signal approximation for linear operation is plus or minus 5 millivolts, or thereabouts. So we have still too big of an input, and we really need to keep it smaller than that. So if we do that, let's see if I can change page again. Okay. So if we keep operation, if Vn is plus or minus 5 millivolts from the Q point. Then we have VGS is plus or minus or is equal to 0.6 0.6 plus or minus 0.005. And that would mean our V overdrive is actually varying from 0.2 plus or minus 0.005, right? That's really what's happening. So if we look on the high end, the largest the current will get, that would be 0.5 times 400 microamps per volt squared times 10 times, so the plus would be 0.205 on V overdrive, 0.205 squared, and we'd get 84.05 microamps, and that would cause a V out, which is VDS, call it plus, is 1.8 minus 84.05 e to the minus 6, you can't read that, times 17,500. That equals 0.329 volts. That's the highest we would go. And then on the minus side, ID minus would be 0.5 times 400 e to the minus 6 times 10 times, so 0.2 minus 5 millivolts gets us to 0.195 squared, and that gets us 76.05 microamps. What we don't really know is that, well, we can see exactly what happens. So VDS minus is equal to V out minus, and that would be 1.8 minus 76.05 e to the minus 6 times 17,500, and that gets us 0.469. So now we have for the output 0.4 minus 0.71. Is that what we had? Yeah, well, that's what it works out to. Minus 0.071 is less than V out. V out is between that, which is equal to VDS, and that goes the other way to, that's 0.329 is equal to that, is equal to 0.469, or is less than 0.469, which is equal to 0.4 plus 0.069. So we're plus 69 millivolts, and we're minus 71 millivolts. Right? So that's much closer to linear. Our V out is going to be the Q point swinging up 69 millivolts and down 69 millivolts, whereas here we were up 17.6 millivolts and down 18.7 millivolts. So we were changing by plus minus 10 millivolts basically, and we're changing now by plus or minus 5 millivolts or something like that. So it's much closer to linear. It's still not perfectly linear, but I would say it's much closer to linear and much more desirable if we stay in the small signal if we stay in that small signal region. Now, like I say, there's really reasons that you can vary in and out of that.